Okay, hi there. So this is section 3.4, local extrema and the first derivative test. I'm splitting this lesson in half so that we have two shorter videos. In this first video, we are going to be coming up with our new definition for what it means for a function to be increasing or decreasing on an interval. You guys have a previous definition from pre-calc, and we're now going to involve calculus in our new definition. And we're also going to look at identifying where a function is increasing or decreasing, and then kind of sketching the graphs of some functions from that information. So in the next few sections, we're going to be really identifying different characteristics of functions in their graphs and using calculus. And that's kind of building on top of the other ways in the past that we've identified characteristics of different types of functions. But that's going to lead us then into another application of derivatives, and we're going to be studying something called applied optimization. But for this lesson, so 3.4 part 1, I just want to recall our pre-calc definition of increasing and decreasing. So in pre-calculus, you determine the intervals where a function was increasing or decreasing by examining the graph of a function and referring to the definition of increasing and decreasing intervals of a function. Those definitions were, and this looks a little more complicated than it actually is. I'm going to rephrase. So suppose that a function f is defined on an interval from a to b. Notice that's an open interval, meaning a and b, the endpoints are not included. If x sub 1 is strictly less than x sub 2, implies that f of x sub 1 is strictly less than f of x sub 2. For every x sub 1 and x sub 2 in the interval from a to b, then f of x is increasing on the interval from a to b. What did I just say? What does that mean? Right? We have a couple inequalities in there. What that really says is if you were to choose any two values on the interval, any two x values on the interval from a to b, and one of those x values would be less than the other x value. If the outputs that correspond to those x values, so the y coordinates that correspond to those x coordinates, have the relationship that the y coordinate that corresponds to the first x coordinate is less than the y coordinate that corresponds to the second x coordinate, then the function is said to be increasing on that interval. Another way to think of it is, remember, we read graphs from left to right, just like a book. So if on that open interval, as x is getting larger, y is also getting larger, then that means that the function is increasing on that interval. And I'll write that down. So if as x gets larger, and this is on the interval from a to b, y also gets larger. Then the function is increasing on the interval from a to b. Whereas the definition for decreasing on an open interval from a to b is the opposite. Basically, if as x gets larger, y is getting smaller, the y values that correspond to those x values are getting smaller, then the function is said to be decreasing on the interval from a to b. Okay, so those are the definitions that we used in pre-calc and at the beginning of this year. So this is our pre-calc definition. And we kind of fell back on that definition for when we were reading graphs, right? When you're reading the graph, you're reading the graph from left to right, and you and this was back when we were right after we studied limits. And if you're reading the graph from left to right, and if it looked like as x was getting larger, the y values were also getting larger, then you said the interval was increasing. And if as x was getting larger, the y values were getting smaller, then you said the function was decreasing. Now, if as x was getting larger, the y values were staying the same, right? That meant that the function was staying constant, and we said it was neither increasing or decreasing. Different for that definition. So if as x is getting larger, y is getting, or y is staying the same. Depending on what text you are using, it might just identify that as staying constant, but it also might say it's increasing or decreasing depending on the open interval and the function that you're looking at. Okay, so now we're going to use kind of our calculus, or we're going to look at what our new calculus definition is for increasing or decreasing. And that's using this theorem, which is the sign of the derivative. So this is going to be our calculus definition for increasing, decreasing. So suppose that f of x is differentiable on the interval from a to b. That means that you can evaluate the derivative of f of x for every x value that's on the open interval from a to b. If f prime of x is positive for all x on the open interval from a to b, then f is increasing on that interval from a to b. So what that's basically saying is if a function has positive sloping tangent lines on the open interval from a to b, the function is increasing. And if f prime of x is negative for all x on that open interval from a to b, then f is decreasing on the interval from a to b. And what that means is if a function has negative sloping tangent lines on an open interval, then the function is said to be decreasing. Now, what we didn't cover is, well, what if the derivative's equal to 0? And we're going to talk about some of the different cases of what that means. And a function can still, even if there is a horizontal tangent line, right, where the derivative is equal to 0, even if there is a horizontal tangent line on an open interval, it could still mean that the function is increasing or decreasing. And we'll fall back kind of on our pre-calc definition of increasing or decreasing there. But sometimes, and we've studied different functions before, right, where I've asked you to identify where a horizontal tangent line is, the function might actually change from increasing to decreasing or decreasing to increasing whenever you do have a horizontal tangent line. So we're going to look at a few examples now, and we're going to just follow these steps, which is going to lead us to being able to actually sketch the graph of the function that we're working with. So this first function is a polynomial function, right? So we know that from our studies in Algebra 2 and Pre-Calc that polynomial functions are smooth continuous curves. Their graphs are smooth continuous curves. And we're going to figure out kind of what, you guys have graphed polynomials in the past, but we're going to figure out what this polynomial looks like, a rough sketch of it from answering these questions that involve calculus. So first of all, part A asks us to find all the values of x that correspond to horizontal tangent lines. These values occur where the derivative is equal to 0. So if I find the derivative here, So f prime of x will be negative 3x squared plus 3, just using power rule. And for part A, I'm going to set that derivative equal to 0. So if I subtract 3 from each side, divide by negative 3, then I'm left with x squared equals to 1. So I get x is equal to plus or minus 1. Right, so that means x equals to negative 1 or x equals to 1. Those are the two x values where there would be horizontal tangent lines for the function f of x. Part B asks us to use those values for x to find the open intervals on which the function is increasing and the open intervals on which the function is decreasing. And the way that we're going to do that is by making an analysis line. So I'm going to make a line, and I'm going to put negative 1 and 1, so those values where there's horizontal tangent lines, and putting those on the analysis line. And what I'm going to do now is I'm going to choose test values, so I'll use green for my test values, to the left and right of each of those values, because I want to figure out what's happening with the function, whether it's increasing or decreasing to the left and right of each of those horizontal tangent lines. So I'll use negative 2, 0, and 2. Those are going to be my test values. And in order to figure out whether or not the function is increasing or decreasing, right, I'm trying to figure out what type of tangent line is happening at a particular point. So I'm going to evaluate the derivative for each of these test values. So f prime of negative 2, that would be negative 3 times negative 2 squared plus 3, which is negative 9. So the main point is that f prime of negative 2 is equal to a negative value. That means that the function is going to be decreasing to the left of negative 1. And now when I evaluate f prime at 0, well, that's easy. I can see that would just be 3. So we'll have positive sloping tangent lines in between negative 1 and 1. So the graph will end up switching to increasing. And then f prime of positive 2 would also end up being equal to negative 9. And then the graph switches back to decreasing because we would have negative sloping tangent lines to the right of positive 1. This is helpful for us to figure out what the graph of f looks like. So first, let me finish answering part B. I'll switch back to blue here. So the intervals in which the function is increasing. The open intervals. Well, that's between, it looks like negative 1 and 1, right? Between negative 1 and 1, the function will have positive sloping tangent lines. And then the function will be decreasing on, it looks like, 2 separate open intervals. So that first open interval would be negative infinity to negative 1. And then the next open interval would be from 1 to infinity. So there can be multiple intervals where a function is increasing or decreasing. There can also be no intervals where a function is increasing or decreasing. So now in order to do part C and sketch the graph of the function, I know where the function is increasing and decreasing, and that's really helpful. But I'm going to plot 2 points. And the 2 points that I'm going to plot are where the graph is changing from increasing to decreasing and decreasing to increasing. So I'm going to plug, in order to find the y-coordinates that go with the x-coordinates where I had the horizontal tangent lines, I'm going to plug those values into the original function. So f of negative 1 is what is that? That would be 1 minus 3 is -2, so -3. And f prime of +1 would be -1, so 2 equals to 1. So the 2 points that I know where there are horizontal tangent lines, I'm labeling it as points just because they're not intervals, they're points, is at -1, -3, and 1, 1. So I can actually plot those points. Pay attention to the scale. I've given you the scale on here. Now, between -1 and 1, the graph is increasing. I also know that polynomial functions are smooth, continuous graphs, so I want to make sure there's no sharp corners. And then we know from -infinity to -1, the graph will be decreasing, so it'll have to curve up going to -infinity like that. And then from 1 to +infinity, the graph would be decreasing again. So I'm making this as smooth of a curve as I can. I don't know how wide these curves are. I don't exactly know what the end behavior looks like just from identifying where the function is increasing or decreasing. But this is a rough sketch that we're able to come up with just from identifying where the horizontal tangent lines were and where the function was increasing or decreasing. So we're going to go through the same steps with this next function. We'll try a new color. So I want to find all the values where the derivative is equal to 0, which is where all the horizontal tangent lines are. So I need the derivative, which using power rule, that would be 3x squared. So I can set the derivative equal to 0, and we just get that x is equal to 0. Right? There would be a horizontal tangent line at x equals to 0. So same step as for part B. To determine where the function is increasing or decreasing, I'm going to put 0 on the analysis line. And then I'm going to choose test values to the left and right. So I'll use -1 and 1. And I'm plugging those test values into the derivative. So I get +3, which means positive sloping tangent lines. So the function would be increasing from -infinity to 0. And then notice whenever we plug +1 in, we also get +3. So the graph continues to be increasing. Now, there's a horizontal tangent line at x equals to 0. But we're determining the open intervals where the function is increasing or decreasing, and you cannot create an open interval around a point. Also, if we think back to our definition of increasing and decreasing from pre-calc, so for increasing, as x is getting larger, y is also getting larger on an open interval. And we think about the function x cubed minus 2. Well, the x value is directly to the left of 0, right? Like as close to the left of 0 as you could, like -0.00000 something, is going to have a smaller y value than x equals to 0. And if you think of a value directly to the right, very close to the right of 0, like 0.00001, that y value that corresponds to that x value would be slightly larger than at x equals to 0. So the interval over which this function is increasing, because there was no change in the slopes of the tangent lines, right? We have positive sloping tangent lines and positive sloping tangent lines. We just say that the function is increasing from -infinity to +infinity. So over the function's entire domain. And just like before, so you might think, oh, well, how do we graph that? Like, do we just draw a line? Well, no, since we know that there is a horizontal tangent line, that tells us the graph is going to level out at the point where x is equal to 0. And we can find the y-coordinate that goes with 0, x equal to 0, just by plugging in. Right? So at 0, -2, there is a horizontal tangent line. So it means the graph would have to level out. And then also relying on your guys' pre-calc knowledge and your knowledge of graphing using translations, transformations, you are familiar with the parent function x cubed, and that -2 is a shift down. So if anything, you could kind of think about just what you already know and the fact that what we just discovered agrees with what we already know, right? That the function is increasing everywhere, that it kind of levels out because there's a horizontal tangent line at x equals to 0. Okay. And we're going to do one last example for this video, and then I'm going to leave the rest for part 2. Okay, so first of all, the domain of f of x equals to -1/x is all real numbers except x equals to 0, right? Which we could also represent as -∞ to 0 union 0 to infinity. Okay, I'm just pointing that out. The other two functions we were looking at were polynomial functions whose domain was all real numbers. To find the derivative of -1/x, I'm going to rewrite it as -x to the -1st power, so I can apply power rule. So f prime will be 1 times x to the -2nd, which is 1/x squared. Now, for part A, if I try and locate horizontal tangent lines or where the derivative is equal to 0, look at what happens. There's no solutions to that equation. There's no real number that you can plug in for x that would make that a true statement. So there's actually no horizontal tangent lines. Oops. However, that doesn't mean we can't still do an analysis line. I'm not putting the values that would make the derivative equal to 0 on the analysis line, but the function could change whether it's increasing or decreasing to the left or the right of the domain restriction. And you guys know from your studies in pre-calc that domain restriction actually corresponds to a vertical asymptote. And also from our studies of limits at the beginning of the year, right? We know that there's actually a vertical asymptote at x equals to 0. And the function could change what's happening to the left and the right. So I'm going to still choose test values. We're going to plug those test values into our derivative. So increasing to the left of 0, to the left of that vertical asymptote. And also increasing to the right. However, because at x equals to 0, it's actually a point of discontinuity, right? An infinite discontinuity. We're not going to include 0 in our interval, meaning we're not going to have one open interval where the function is increasing. We have to split it up because 0 is not even in the domain. It's a point of discontinuity. So when we list where the function is increasing, we'll say from -∞ to 0, and then as a separate interval from 0 to infinity. And the function isn't decreasing anywhere. Now, to graph this, you do kind of need to rely on your previous knowledge. Like just from studying rational functions in pre-calc and from studying limits, right? The limits allowed us to determine some characteristics about functions like end behavior and points of discontinuity. So from all of that prior knowledge, you guys know there's a vertical asymptote at x equals to 0, and there's a horizontal asymptote at y equals to 0. Because as x approaches positive and negative infinity, this function would approach 0. So to the left, I'm using orange, to the left of 0, the function is increasing. And just from what you guys know about, you could do a test point, right? If we plugged in -1, right, that would end up giving us the point -1, 1. And we know the function's increasing, so we could kind of go off of that. We're also going to continue, and then if we plug in 1, we'd have 1, -1. So we're going to talk about more ways to identify characteristics that will help us understand a function's graph. So going forward in part 2 of this section, but then also the next couple sections. Okay, so this was really getting an idea of what some of these pretty basic functions look like from identifying where they are increasing and decreasing based on the slope.